Hi, everyone. Our next topic is the inference on correlation and regression coefficients. So we'll be testing a hypothesis revolving around correlation coefficients and regression coefficients. So we will be starting with correlation, inferences on correlation coefficients. Then later on, or in the next lecture, we'll be talking about inferences on regression coefficients. So let's recall. Let's start with inference on correlation. Inference on correlation coefficients. Let's start by recalling a few things. So let's recall that the relationship, sometimes called association, the association between two variables, between two random variables, between two variables. For convenience, let's call them x and y. Between two variables x and y is summarized by the value of the sample correlation So we're just talking about the descriptive. So the descriptive value is the sample correlation, and the sample correlation is defined as the sample correlation coefficient. Sorry, here I should have said sample correlation coefficient. It's a summary value. So the sample correlation coefficient, denoted by R, is defined as, so that's how we define the sample correlation coefficient. We say that R is equal to, covariance of x and y divided by square root. Then we have variance of x multiplied by the variance of y. In words, that's how you define it. Square root, the divisor is the square root of those two guys. So, which is the same as, in symbols, we can have it like this, divided by the square root s squared of x multiplied by s squared of x multiplied by s squared of y. Okay, so this sometimes is also written as summation of x minus x bar minus y bar divided by the square root of summation of x minus x bar squared multiplied by summation of y minus y bar squared, like that. And we know that there are some things we can simplify that expression by saying that we know that summation of x minus x bar squared is the same as summation of x squared minus n x bar squared. And that means you can also have a similar expression for the deviations of y squared. And then number two, we can also have summation of x minus x bar multiplied by y minus y bar is the same as summation of xy minus n x bar y bar. Yeah, like that. So we can have, so we can replace, we can rewrite this expression here using this more information we have here. Okay, so I think you can, it is easy for you to simplify that. Okay, then we also note that we note further that R, the correlation coefficient here, R, is always a number between -1 and +1. Is always a number between -1 and +1. Okay, so that's number one. The number two, we also need to note that R is a measure R is a measure of the linear association between the variables, but does not give the cause in quotes, the cause and effect, or the cause effect kind of relationship. It does not give that kind of relationship. As you know, that kind of relationship is given through regression analysis. Then Roman 3 under the notes is that two variables, and these are caution that two variables may be statistically related or correlated, but not directly causally, from the word cause, causally related. So we're saying that it is possible for two variables to have very high or significant correlations, but you find that they do not have this kind of relationship. They are not causally related. They are not directly causally related. Okay. So we say that this is called spurious. This is called spurious correlation. It's called spurious correlation, and it occurs when the relationship is being driven, when the relationship between the variables is being driven by an unseen third party or third variable. If there's a third variable which is not being considered here, but is the one driving the strength of the relationship, third party, like that. So it can happen that the variables seem to be having some relationship, but you find that that kind of relationship is just driven by a third variable. And that third variable in most of the cases will be time. So you find that every variable is changing with time. So when you plot them, you feel that, or it gives the impression that they are highly correlated. But in the real sense, if you were to remove the effect of time from the measurements, then you notice that the two variables may not actually be significantly related. So when dealing with correlation, is very good for you to be cautious about this. It's very good for you to be cautious about this, to verify whether the kind of relationship we have there is actually a real relationship or is a fake relationship. Because it will be a fake relationship if it is masked by some other, or if it is being driven by what you're calling a confounding factor in this case. Okay, so let's go to the bit on inference, the inference on correlation coefficients. And we're going to have two scenarios. Number one, under the null hypothesis, that H naught, that rho is the population correlation coefficient, is equal to 0. Under that null hypothesis, which means that the two variables are not correlated, they're independent. They are not correlated at all. So where rho is the population correlation coefficient, is the population correlation coefficient, comma, we define this item here, that R multiplied by n minus 2, divide everything by the square root of 1 minus R squared. So that item, as you can see, we're just using R and the sample size. So this item here has a t distribution. as a T distribution with degrees of freedom nu given by n minus 2 with or v is equal to n minus 2 degrees of freedom. With n minus 2 degrees of freedom, where R is the sample correlation coefficient. The sample correlation coefficient. Okay. So we note that this hypothesis tests that, or tests the situation that, in quotes, there is no relationship. There is no relationship between the two variables. So if there's no relationship between the two variables, it means that the correlation is equal to 0. Because also covariance will be equal to 0 in that case. So that's the hypothesis we are testing. There is no relationship between the two variables. Then of course, the alternative hypothesis can take any of the three formats explained a little bit earlier. Okay, so that's the first scenario, number one. The second scenario is when we try to generalize that. When we generalize that situation, we say that, or this we call this one the general null hypothesis. That means that the rho is not necessarily set to equal to 0. So if rho is not necessarily set to 0, that's what we're calling the general null hypothesis. And this is called the Fisher's transformation of R. The Fisher's transformation. So we use the Fisher's transformation of the sample correlation coefficient there. Okay, so let's consider the item here. W is equal to half. Then we have ln, the natural logarithm, 1 plus r divided by 1 minus r. You can put them in brackets like that. Ln, so that's the natural logarithm. So if you consider that, we say that then W, it can be shown that W has approximately normal distribution, with mean, where the mean is given by, we can denote it by mu of W being equal to 1 over 2. Then we have ln 1 plus rho divided by 1 minus rho. So we find that the formula looks quite similar to what we have here, but now here we're using the hypothetical population mean, rho. We're using the hypothetical population mean, rho. And standard deviation given by, you can call it rho of W given by 1 over square root of n minus 3. So once you know that W has approximately a normal distribution, then it becomes quite easy for us to test the hypothesis. Okay. So we say that this is usually called the Fisher Z transformation. The Fisher Z transformation, because the resulting Z values are approximately normal. Because the resulting Z values are approximately normal. So as a result, the letter Z is generally used. So the letter Z is generally used. Okay. So there's a quick way of obtaining this Z, or this value of Z here, or W, using your calculators. So I want us to note it down. So we say that W, we note that W or Z here is the inverse hyperbolic tangent. Is the inverse hyperbolic tangent function, and can easily be obtained from your calculators. From most, let's say from most scientific calculators, by pressing, you press this function here. You press that of R, where R is the sample correlation coefficient. So you press that, and this is usually found under this function in your calculator, the hyperbolic function. The hyperbolic function, no? It's just written like this on your calculator. Let's say function. Okay, we'll be using it in the example. Okay, but I think many of you have come across this item here when you are doing trigonometry or something like that. Then we say that using the results of W, we can test now this general hypothesis, H naught, that rho, now instead of saying is equal to 0, we get a general value there, is equal to some hypothetical constant there, and then based on the argument above, it is also good to note that we can also obtain confidence intervals. But for now, this is not our interest. We can also obtain confidence intervals for the mu of W and rho. We can also obtain that. But our focus now is the testing of hypothesis. Okay, so let's have some quick example. You are given n is equal to 10. Then you are given R is 0.958. And then you are told to test the hypothesis. Test the hypothesis that H naught, that rho is 0.9 versus H1, that rho is bigger than 0.9. So let's test that hypothesis. So let's solve this example. So we say solution. We need the test statistics here. So we need W, and we shall be using the calculators to quickly obtain these values. So this is H1. So we shall be using the calculators, and we said that use the function usually in small letters. So this hyperbolic function, HYP. So once you press this, you will see this screen. You will see a screen containing several things. Let me list a few of the things that you will find there. So once you press your calculators, you will see this window. You will see these. So the function we are looking for is, sorry, this is number 5 and 6. So we are looking for this function here. So for you to retrieve it, you press number 6 on the keypad. So once you do that, that will prompt you. You will see this, the bracket. So that will prompt you to put the correlation coefficient. And remember, we are obtaining W using the sample value. So here you type 0.958 close brackets. So which will give us 1.921. So this is the value we're talking about, 1.921. So that's our value of W. Okay. Then in a similar way, we obtain the mu of W, the mean there. Remember, it is similar to W, but now we are using a rho is 0.9. So this one we used R is 0.985. So that's the only difference. So we repeat the same procedure. So you go to the hyperbolic function, you choose number 6, then you type 0.9 close brackets, you'll get 1.4722, something like that. Then sigma, we know it is 1 divided by square root of n minus 3. So this will be 1 over square root of 10 minus 3, which is 7, which is, so the answer there is, so we'll get 0.3779 something, 96 etc. Okay, so those are the values that we need in order to test the hypothesis in question. Okay, so from there, now we proceed. So therefore, the probability that W is bigger than 1.921, we're looking for that probability. That probability is so that statement is gated by the alternative hypothesis that we are testing. So from there we can use the standardized value of W. Remember, if we were dealing with something like this, X is bigger than, let's say, 1.96, and we already know that mu, mu is let's say 1.47, and we know that sigma is 0. We are dealing with a situation like that. So we know that the standardized value of X is given by this, divided by that. So we shall use the same analogy to define a standardized value of W, to obtain a standardized value of W as follows. So this is equivalent to, the probability that, now we use a Z, is bigger than 1.921 minus the hypothetical value, mean of the population, 1.4722, divided by the standard deviation, 0.3, let's say 78. So we're looking for that probability. So when you simplify that, you'll get this the same as probability that Z is bigger than 1.19. And we can obtain that value from either the tables, or we can use R to quickly obtain that value. So using R, we obtain that this probability is equal to 0.1170, something like that. 233, 232, looks like that. Okay. So this value here is the p-value for the test statistic in question. So this is this area here. So if that is the p-value, we observe that, we conclude that the p-value probability value for R is 0.958. For that calculated value is 0.1170232. So as clearly you can see, that p-value is quite large if you were to assume the 5% level of significance. Hence, there is insufficient. There is insufficient evidence. There is insufficient evidence to justify rejecting H naught that that rho is equal to 0. So we fail to reject that. So that means that the two variables x and y are actually not correlated in a significant way. They are not correlated in a significant way. So any question there? So let's look at this example. You'll try this at home, then you'll share the answers with me. Yeah? So a new computerized ultrasound scanning technique has enabled doctors to monitor the weights of unborn babies. The table below shows the estimated weights for one particular fetus at fortnightly intervals during the pregnancy. So you have the data there, where in the first row we have the gestation period in weeks from week 30 to week 40. Then in row 2, we have the estimated weights of the unborn children, of the unborn child in kgs. Okay. Then you are required to, number one, to perform a test of the null hypothesis that rho is equal to 0 against the alternative hypothesis that rho is greater than 0. Okay, so this is you will use the first scenario. You can actually use both and check whether the conclusions will be the same. You can use this assumption. You can use this scenario. So the first case here. So you can use this case because actually that's what the null hypothesis is stating. But you can also use the other one because the other one is general. So then you can compare whether the conclusions will be the same or different. So you can use this test statistic where you'll use a t statistic, then you make out your conclusion. Then you can also apply this. You can also apply this method. Then the second part of the question, you are asked to test whether, you're required to test whether the data supports the hypothesis that the correlation parameter is greater than 0.9. Remember, the correlation parameter is this guy. So we want to test whether it is 0. So that should be your H1. Then your H naught should be that your rho is 0.9. So do that exercise, then you can share the answers with me after the class. That marks the end of today's class. Any question?